In this video, we'll talk about some more terminology and definitions with regards to linear algebra topics and see how they connect what we've already discussed previously about solving systems, in particular solving homogeneous systems. So if I have vectors v1 through vn, whatever they happen to be, any dimensional vectors that I want, a linear combination of these vectors is a new vector v that is written in the form v is c1 times v1 plus c2 times v2 plus cn times vn for constants, real constants, c1 through cn. The idea of linear combinations is that I'm basically taking some number of v1s plus some number of v2s plus some number of v3s and adding them all up to get this new vector that is a combination of v1 through vn with certain constants on it. Now to follow on from this, if I let v1 through vm be any set of vectors in Rn, these are n component vectors because the n up here, but I have m of them. The span of these vectors is the set of all linear combinations of those vectors. So it's all vectors in Rn that can be written as c1v1 plus c2v2 plus c2vm for some choice of constants, c1 through cm. So it's a lot of vectors, infinitely many vectors. It's all that I can write of this form. So as an example, if I take my v1 to be the vector 1, 0, 0, and my v2 to be the vector 0, 1, 0, then I know for a fact that the vector 2, 3, 0 is in the span of v1 and v2. How do I know that? I know that because 2, 3, 0 I can write as 2 times v1 plus 3 times v2. If I take 2 of these guys, it puts a 2 in the first component, and 3 of these guys puts 3 in the second, gives me exactly the vector that I want here. What I could say beyond that is that any vector is that any 3-component vector that has a 0 in the third component is in this span for the exact same reason as above. As long as I have a 0 in this spot, the vector a, b, 0, I can write as a, v1 plus b, v2, and so this vector is always in this span for any choice of a and b. So the span is big. It has a lot of vectors in it. So a related definition to this is that of a spanning set, which kind of goes in the other direction. So if we take, say, our vector space Rn, right, the set of all n component real vectors, we say that a collection of vectors, v1 up through vm, is a spanning set for Rn if these vectors are all in Rn and their span equals Rn. The idea here is I have a spanning set if it is possible to get every vector in Rn as a linear combination of these v1 through vm. If they sort of are different enough that they cover everything, then we say we have a spanning set for this vector space Rn. We'll come back to this idea a little bit later. For now, though, we want to take this in a slightly different direction. And that's the idea of linear independence. So we talked about this term a little bit before, but kind of indirectly in talking about second-order equations and how to find solutions to them. We want things to be different enough to make things work out nicely. Now I want to have a concrete idea of what we mean by different enough. And so we say that vectors v1 through vn are linearly independent if the only way to satisfy the equation c1 times v1 plus c2 times v2 plus cn times vn equals 0 is by picking all of the c's to be 0. That is, there is no linear combination of the v's that equals 0 unless I pick every single constant to be 0. And I wrote here non-trivial linear combination because if we pick the c's all to be 0, we get 0 no matter what. So what we're looking for is there another combination that gives me 0, and if not, we say the vectors are linearly independent. So otherwise, if this is not the case, that is, there is some other combination that makes it 0, we say they are linearly dependent. Let's see, in terms of an example, what this looks like. So are the vectors 1, -1 and 0, -1 linearly independent? Let's answer that one first. So to look at this, I want to see, is there a choice of C1 and C2 so that C1 times the vector 1, -1 plus C2 times the vector 0, 1 equals the 0 vector. Because if I can pick C1 and C2 not both 0 such that this is true, then they will be linearly dependent. But we can write this out as a system of equations. This becomes C1 plus 0 C2 equals 0, and negative C1 plus C2 equals 0. And we can easily see by inspection that the only solution is C1 equals 0 and C2 equals 0. Therefore, there is no such choice. And so, yes, these are, in fact, linearly independent. What about this second set? We have the set 1, 1, 3, 2, and 2, 1. So there's two ways to approach this. One is by just staring at the vectors. And if you look at them, you can see that 3, 2 minus 2, 1 minus 1, 1 in fact equals 0. So this is a linear combination of those three vectors that gives me 0. Therefore, they're linearly dependent. So this here should be a no. But let's look a little more formally at what might cause this. Let's write out this system here in terms of these coefficients C1, C2, and C3 now, and see what we get. So if I want to look for linear independence, I want to look at C1, C2, and C3 so that C1 times 1, 1 plus C2 times 3, 2 plus C3 times 2, 1 equals 0, 0. And if we write this out, we will see that I want to solve the system. C1 plus 3C2 plus 2C3 is 0. C1 plus 2C2 plus C3 equals 0. We see at the outset we have two equations, three unknowns. It is likely underdetermined. Therefore, there should be non-zero solutions. We could also put this in the augmented matrix form and reduce the matrix. And we'll see that because we have zeros on the right, we can drop that part. 1, 3, 2, 1, 2, 1. I can reduce that one step. 1, 3, 2, 0, minus 1, minus 1. And we'll see here a non-pivot column, which you should expect because we only had 2 rows and 3 columns in the first place. And so we'll end up with a free variable giving us non-zero solutions. And so we'll again get that these are linearly dependent. And what do we see here? Well, from this, linear independence comes down to solving a homogeneous system of equations because we're looking for values for C1, C2 up to Cn such that that linear combination becomes a 0 vector. Or if I write it on matrix form, I could look at this system C1 V1 plus C2 V2 plus Cn Vn equaling 0. I can rewrite as A times the C vector equals the 0 vector, where C is the vector of the C1 through Cn, and A is the matrix whose columns are the vectors V1 through Vn, which I will notate this way. The point being the columns are the vectors V1 through Vn. And so what this really comes down to, as we saw before, is just this matrix A. Right? The C here is kind of unimportant. It's the variable we're trying to solve for, but it's not an integral part of the problem. The integral part of the problem that tells us what's going on here is the matrix A. What we can do is row reduce the matrix A and see what happens. Right? And we get A by putting the vectors V into the columns of this matrix. Now what we're looking for here is non-pivot columns. Because we know we have a homogeneous system, so a non-pivot columns cannot mean inconsistent. It means under determined, where it means that I have a free variable. And we have a free variable, and in particular, that column where you got this free variable can be written as a linear combination of the other columns in the matrix, or the other vectors in your list. So that column vector can be written as a linear combination of the other vectors in your set. For a secondary approach to analyze this problem, you could also put the vectors in as the rows of the matrix A. If you do this, then the elementary row operations are just doing linear combinations, and so you'll see that if you get any 0 rows, that means you did a linear combination that got you to 0, in which case a 0 row indicates linear dependence. There's really benefits to both of these approaches depending on what you're looking for in a problem, but in both cases they can indicate whether or not sets are linearly independent, how to work things out. The columns approach gives you an easy way to determine which ones you can throw out of your set because that is linearly independent. The rows approach will let you get a simpler characterization of the spanning set for what you're left with. So there is the idea of spans and linear independence and how we can use solutions to homogeneous systems of equations in order to analyze these properties.